Since this course is about general chemistry, organic chemistry, and biochemistry, we are going to look at the three different ways that these different fields of chemistry look at chemical equations. A general chemical equation has the chemical formula only, and then we indicate reversibility and the conditions through the arrow. So these are the type of chemical equations that we saw in Chapter 1, and here's an example of a chemical equation that represents the combustion of propane. And we see from this arrow that this is an irreversible chemical reaction. In organic chemistry, we really care about the functional group. So we typically are going to draw out the structure of the organic molecule that is reacting so we can really see what is happening in the reaction. And then our arrow does still indicate reversibility, but we also include small reactants, so reactants that aren't that interesting to organic chemists, as well as the conditions. So here's an example of an organic equation where we have the structure of the molecule written out so we can clearly see there's a double bond. The arrow actually has one of the reactants above it, hydrogen. Hydrogen is reacting, but it's not that interesting, so we just place it above the arrow, and then we also see that a platinum catalyst is necessary. The product is also written as a structure, so we can clearly see that from beginning to end, we have lost our double bond, and our alkene has transformed into an alkane through the addition of hydrogen. And then in a biochemical reaction, we also care about the structure. So we're going to draw the structure of the organic molecule of interest. And in biochemical reactions, there are often what are known as coupled reactions. For example, we get energy from a reaction that's occurring at the same time. So let's look at this reaction where glucose forms glucose 6-phosphate. And we notice this is not a balanced chemical equation because on the left, the structure of glucose is different on the right than glucose 6-phosphate. Glucose has this phosphate functional group attached to it. Where did it come from? Well, phosphate functional groups come from ATP. ATP has 3 phosphate groups, and when it donates a phosphate group to a biochemical such as glucose, it loses this phosphate and goes to adenine diphosphate. So ATP has 3 phosphates, ADP has 2 phosphates. This is a very common reaction, and not only did glucose gain phosphate, so this is actually a synthesis reaction where glucose plus phosphate are added together to get a product, but because it's a synthesis reaction, the delta G is positive and energy is necessary. When ATP transforms to ADP, energy is released. And this happens so often that biochemists know that this process releases energy. And so this is a coupled reaction. Glucose forms glucose 6-phosphate, and then ATP transforms to ADP. It donates that phosphate as well as energy. So this coupled reaction is drawn above the arrow, and also the enzyme required for this process, hexokinase, is written as well. So how we write out a chemical reaction will depend on what sort of information we're trying to get from that chemical equation.